So welcome to Lab 3 of EE100 Engineering Laboratory. And what we want to do in this lab is to give you an introduction to something called signals. Okay, and we're going to talk about what signals are, and an introduction to something called analog to digital conversion. And in that process, while we're trying to teach you those concepts, we're going to have some fun with audio signals. So all of the lab tasks that we're going to see, they would deal with audio signals, and in dealing with that audio signals, we're going to try to teach you those some abstract concepts as well. Okay. How many of you are familiar with the term called analog to digital conversion? I mean, it's self-explanatory. Let's see if somebody can try to explain what analog to digital conversion is. So who's going to volunteer? Are there volunteers or should I pick somebody up? Yes, Daniel, go ahead.
So analog signals are basically those signals that can be understood by humans.
Okay.
And digital signals or anything being digital would be something in form of digits that may not be comprehensible by humans, but may be comprehensible by machines.
Okay. So that's an excellent point. So I'm going to come back to this in a bit. Hania, you raised your hand. Go ahead.
Analog signals are continuous values, but digital are discrete, and they're just 0 and 1.
Okay, excellent. Isra, go ahead.
Yes, sir. Analog to digital converter is something, just say like we can change a voltage into digital signals, such as in the binary forms and all.
Right. Very nice. And Irtaza, go ahead.
Yeah, so from my understanding, an analog signal usually refers to a signal which is usually continuous in nature, as in it can be usually mathematically defined as some form of function. A digital signal, on the other hand, involves a combination of discrete values, usually in the form of zeros and ones, which is how we use the binary number system. Right? Okay. So usually analog to digital conversion involves converting that mathematical function into certain discrete values which are close to the analog value equivalent.
Okay, all right. So, so it looks like I mean, you have a good idea of what analog signals are and what digital signals are. So let's wrap this up, right? Let's finish up this lab and we're done. Let's go to the lab task, right? But nevertheless, so I do want to say something about what, for example, you can see my screen, right? Lab screen, can you see that, right? Okay. So yes, what Daniel said, for example, Daniel said the continuous signals are, or analog signals are something that humans can understand, right? And digital signals are something that the machine can understand. That's a misconception that I would like to clear in this, because we would like to understand what digital signals are, and there's an entire theory behind it which would allow you to understand what digital signals are, and that's what we're going to do here as well. So actually, all of the signals that you're going to see in this lab, or you have seen in this lab already, they are digital signals. So the data that you looked at for COVID-19, that was actually, we would say that's a digital signal as far as our lingo is concerned, as far as our jargon is concerned. Okay. There's another point that Irtaza made, which was analog signals are which can be mathematically described, and digital signals are not necessarily mathematically described. That's also a misconception that I would want to clear at this point, and in the lab as well, as we will see that digital signals will also be, we will also be able to describe this as digital signals in mathematical form. Okay, so let's begin, right? So what I want to do here first off is, if you recall the data definitions that we had in the last lab, right? So there were two initial definitions. We said this is factual information, which is used as basis for reasoning or for discussion or calculation, or is information in digital form that can be transmitted or processed. However, what we will be mostly dealing with in EE100 is this third definition, which I think is extremely important. And this definition just says that the data is information which is output by a sensing device or an organ that includes both useful and irrelevant or redundant information and must be processed to be meaningful, right? And more or less, all of the labs that we're going to see from here on is will have to do something or the other, and those will go back to this definition. So we're going to be dealing with information which is output by a sensing device, right? And the simplest example of that we're going to be dealing with is the output of a sensing device called a microphone, and which is nothing but your speech, or which is nothing but the audio. Okay? And we're going to be dealing with many other signals as well. At the same time, that information that we extract from that sensing device may have some meaningful information, may have some useful things, or may have some irrelevant things as well. And our job is going to be trying to extract some meaningful inferences or meaningful data or meaningful information from that seemingly unmeaningful data or seemingly unmeaningful signal, right? So this third definition is what once again struck me when I was reading up these definitions, in the sense that this is very relevant to what our course objectives are. Okay, so an example of something like this is ECG, and this is what I talked about as well. So if you go back to lab 1, this is the graphic that I showed you there. So you have a smartwatch, you may have ECG sensors on your smartwatch, although typically ECG sensors are actually placed on your chest, and they actually measure the electrical activity that your heart generates, and transforms that into this form. So this is an actual ECG signal that we've recorded using LUMS hardware. And what you see is that ECG signal or ECG information is actually a function, or if that's a curve of voltage on the y-axis and time on the x-axis. So this is some function of time, right? So this is voltage function versus time, right? The other example I can give you, and which is something we're going to be dealing with this in this lab, is speech, right, or sound. So as I speak, how is my sound generated? Anybody? I mean, how do I speak? I mean, किस तरह बोलता है बंदा?
Sir, through waves, yeah, your sound is transmitted from media.
So through waves, and the way those waves are generated are actually through your vocal cords, right? So your vocal cords actually vibrate. So when you want to speak, your brain transmits a message through your vocal cords, and your vocal cords actually vibrate. And it is because of those vibrations, that the waves actually travel from your mouth to somebody's ear or to your microphone, right? So as the waves travel through a certain point in time, you actually have pressures going up, or the pressure at a particular point going up and going down, right? So if you record that pressure as a function of time, I would say that's a signal, right? So because that's a plot, that's a function of pressure versus time. Now the same pressure as it, or the wave as it is incident upon a microphone, what does the microphone do? Anybody else? Ashar? So not Qasim, if you allow me to have other people involved, sorry for that. I'm going to pick on people now. Ashar, how do you think the microphone works? Ashar Javed, are you there?
Yes, sir.
How do you think a microphone works?
So the vibrations of the sound, I think, hit a diaphragm, and it vibrates and generates signals.
Okay. What do you mean by that? It generates a signal.
Like it generates a signal which the computer reads and then transfers to digital.
Okay, so it generates a signal. Okay, nice. So if somebody else raised their hand as well here, who did? If they can raise it again, so I will not pick on people then. Yes, Qasim, go ahead. Qasim Rashid, go ahead, please.
Sorry. Yes, sir. Sir, I think that microphone, like, it works in the way that it converts the electrical signals or the electrical currents that are coming towards it in form of waves.
Okay, so what you're saying is actually what happens is the opposite. It actually converts the waves into electrical signals, right? So your microphones have something called a piezoelectric material, or a piezoelectric sensor, if you will, right? and it's connected to some electric circuitry. And what happens is, as the waves hit that piezoelectric material, that vibrates. And that vibration or that movement causes electricity to be generated, and that creates signals in the form of voltage or currents, right? So piezoelectric converts mechanical energy, which is in the form of the pressure waves that insert upon it, into electrical energy that we see as a function of time. Okay, so that's how basically a microphone works, right? And if I were to, so the curve that you see on your screen here is actually my own speech, which I zoomed in for about 0.2 seconds or 0.3 seconds. So this is what the microphone output actually looks like as I am speaking. Okay, so I would say that this is a signal, right? In the sense that because this conveys some meaningful information about some physical phenomena, which in this case is some pressure waves, or which in this case is some electrical activity, as a function of time, right? As a function of time. So this is once again voltage versus time. Okay, and so this is to give you an idea of what a speech signal looks like, right? So this once again is the output of a microphone, which is voltage versus time. So time on the x-axis and electrical voltage on the y-axis. And if I can just play this for you, because this is an audio that you're going to keep on hearing over and over again in all of the lab tasks. So let me just play it for you, and then I'm going to have something else to say about this. Okay.
प्यारे बच्चों, मेरी आवाज़ सुनो और सुनते चले जाओ.
Right. So I hope you were able to hear the sound. Can the TAs give me a thumbs up? Okay. Right. So, I mean, when I look at the graph, I mean, this excites me so much. Yeah, I mean, this is what I spoke, and this is what it looks like. So I was able to visualize what I was speaking in the form of this nice looking, for me at least, some visualization of what the signal or what the audio speech looks like. And I can map those to each and every one of the words, roughly speaking, what I was saying, right? So, yes, that is my voice, Jazlan, and this is my voice that you're going to keep on hearing over and over again in the lab task as well, and some of my daughters as well. So I mean, there's a point I want to make there when you do that lab task, okay? All right, so I'm going to ignore Kiran's comment, and so I can map this to words, right? So the first thing, can you see my cursor? Hassan, can you give me a thumbs up? Right, so you can see the cursor. Right, so this is, roughly speaking, based on my understanding, this is what pyare looks like, right? And you can map each and every word to a certain waveform, and that should give you an idea. That's how speech recognition systems work, right? So pyare is going to look like something, right? And speech recognition is going to try to recognize, try to learn what pyare looks like, and translate that audio signal into the word pyare, okay? And then there's a bacho here, the meri awaaz suno here, and then I take a pause for a while, and you clearly see that when you, so pyare bacho, meri awaaz suno, and then I have a little bit of a pause. And this is that where that pause is, where that gap is, right? And you can clearly see that when you don't speak, you actually see a signal which is close to zero. And when you speak up, when you speak loudly, this signal is higher. When you speak low, less loudly or in hushed tones, this signal is going to be lower, right? So there seems to be one-on-one correspondence with what you're speaking and what you're observing, okay? Now, one of the important points here is that this signal that you see here is actually a electrical voltage versus time, actually, right? As a function of time. But there's the one-on-one correspondence of the sound pressure versus time as well. There's a one-on-one correspondence of this signal with a pressure signal, because your piezoelectric material ideally works in a proportional sense. In the sense, higher the pressure, or the pressure is proportionally converted to a voltage. So I can go back and forth between the pressure signal and the electrical signal. So signals can be converted from one form to the other. So this is something that the thing that you see on your screen is a signal. This is a speech signal that we're going to be working with a whole lot. Okay. So now let me just go back and just define some abstract definitions. So what is a signal? So signal, very, very roughly speaking, I think this is maybe from Wikipedia, that the signal is a function of time that conveys information about some physical phenomena, right? So the ECG signal that you saw, that's a signal because that conveys some information, physical information, or a physical phenomena as a function of time, right? The speech is a signal, as you saw earlier. Other examples are biomedical signals, which not only include ECG, and there's a couple of other examples that I gave in the handout. EMG signals is another example. Are you guys familiar with EMG? EMGs, anybody? Who's familiar with EMG or EEG?
Is it the thing that you do with the heart? Like,
so the
the
heart
test,
thing is
EEG?
ECG, electrocardiogram, right? EMG is I forget the name, some myograph or something, right? And yes, Irfana, go ahead.
Electroencephalograph, the one which measures brain signals.
So that's EEG. Okay, very nice. Right. So EMG is a signal which measures your signals off of your muscles. Okay, so when you move.
Yeah, sir. It's something related to the muscles and all, nerves and muscles.
Good. So as I move my muscles here, so if I place an electrode here, which can try to detect electrical signals, and this is one of the first SPROT FYP that we did when I joined LUMS back in 2010. It can try to detect whether you're closing your hands or whether you're opening your hands. And it can actually go the other way around as well. If you do that stimulation in electrical signals, you can involuntarily move somebody's hand. And I maybe share a video or the TED talk in which people try to control another person's movement through their brain. And the way they do that is the brain also generates electrical signals. And those are called EEG signals, right? And those EEG signals you can try to detect and figure out whether that person is thinking of moving or not. And you transmit that information and sense of electrical signals to somebody else's hand. And I'll show you the real-time demo in the form of a TED talk and perhaps over email, right? Maybe sometime later. Other examples are GPS signals or seismic signals. Seismic signals are signals that you measure, that actually measure the vibration in Earth, right? And that's basically a detection of whether an earthquake took place or not, and how much of an intensity was that earthquake. And more importantly, researchers try to use those seismic signals to try to predict whether an earthquake is going to happen in the future or not, right? Other examples are radar signals and radio signals, and we can go on, and each one of them have very, very interesting applications in there for each one of those signals, okay? And then there's, if you know what signals are, then there's something called signal processing, right? Which is, as you see on the screen, is mathematical manipulation. So mathematics is extremely important here. So there's a mathematical manipulation of an input signal so as to either obtain some information or insights or decision in the sense, okay, lockdown khulna ya nahi khulna, right? As we would have done in lab 2, or whether there's some abnormality in the heart or not, or whether you're trying to think of a certain alphabet or not, so not exactly that, but are you trying to think of moving your right arm or your left arm, and so on and so forth. So those are the kind of decisions that you can try to make with those input signals. At the same time, you could have signals which are input and the outputs are also signals, in the sense that you would want the output signals to be some refined version, right? Some refined version of the input signal, right? So and the simplest example I can give you is for that COVID-19 data. You would have seen some random fluctuations there, and you would want to smooth out those fluctuations. And we're going to see a lot more in the next lab, for example. We're going to try to see, can you separate my voice from some dogs barking, for example, right? And so that's a processing that you would want. Okay, input pe signal hai, output pe signal chahiye, but that output signal is a refined version because my voice is hopefully more refined than a dog's, right? And so it's a refined version of the input signal, right? So this is roughly speaking what the domain of signal processing is, and it's an entire domain. You can have, and lots of us in the electrical engineering department actually specialize in broadly speaking in this domain, right? And that's more or less the agenda for the rest of the semester. We're going to work with signal processing for many different applications, right? Now, one point here is that there's loads of exciting, and I really want to emphasize this here, it's exciting mathematical foundations behind signal processing, right? But we, as considering the fact this is a freshman course and this is a 1 credit hour course, we will not be able to have all of that excitement. I will not be able to share all of that excitement with you in this semester. But we do have all of that excitement in Hassan and Isha and Hamza. All of them have gone through that excitement with me in some of my courses. Okay. So nevertheless, so that's mathematical foundations. We're just going to touch upon them. We're going to try to give you a very, very intuitive understanding of what it does, but we will not delve too much into rigorous mathematical foundations as far as this course is concerned. Okay. Now, what is the simplest signal? Simplest signal is a sinusoid. Okay, as I'm sure each and every one of you is familiar with, right? Sinusoid is just this is the thing that you see on the screen, right? A sinusoid is characterized by its amplitude, its phase, and its frequency, right? So the phase that of the sinusoid that you see here is 0, and the amplitude is 1. But what's important is the frequency of the sinusoid, right? So what is the frequency of a sinusoid? How would you define a frequency in hertz, for example? Ji Iman Bilal.
Sure, can I answer?
Qasim, let me see if Iman can answer. Iman Bilal.
Sir, could you repeat the question? You're asking how you'll describe the wave in terms of its frequency.
So if you were to explain what a frequency is to my 12-year-old son, I mean, how would you explain it to him?
It's the number of cycles of a particular wave, or the number of cycles of something that happens in a unit time. For example,
Okay.
a second.
Excellent, right? Or the number of times something repeats itself.
In a fixed
in a unit time, right? The number of times something happens, right? So that's frequency, okay? And the frequency for this sinusoid is, in terms of the variable, is f hertz, right? Which corresponds to a time period, which is 1 by f seconds, right? And that 1 by f seconds is something called the time period. And this is the time that it takes for the sinusoid to complete one revolution, if you will, right? Or to complete one cycle. Okay. Qasim, go ahead. You want to say something?
Sir, I think it's answered.
Okay. Very nice. Right. So the time period is in seconds and the frequency is in hertz, and there's an inverse relationship between the two. Okay. Now, the reason why I bring this up is because let's try to see what these sinusoids sound like. Okay. So this is a sinusoid that you would be familiar with visually speaking. Now we're trying to perceive those sinusoids through our ears and not through our eyes. Okay, so this is a sinusoid that you're going to hear, which has been generated at 500 hertz. Okay, so here's what the sinusoid sounds like. Right, so it's 5 seconds of data. It's 5 seconds of a sinusoid which repeats itself after every 2 milliseconds, okay? And it is a tone, right? So this is called a tone, if you will, in audio terminology. It's a tone. It's a flat tone, right? And maybe if some of you are music enthusiasts, I mean, all of the music tones or music notes, if you will, are actually made up of these tones. I mean, you combine different tones together, or different frequencies, tones जो है वो मिला के different musical notes बनाते हैं, A sharp, B sharp, C sharp, whatever, right? I'm not very comfortable with that. Okay, so Hania, can you share down what you mean by something went wrong? Okay, so nice to see. Right, so let me. So it's not something went wrong. It's actually a tone. It's a flat tone of 500 hertz. Okay, let's try this out for 1000 hertz. So Hania, what do you expect? 1000 hertz की चीज क्या दिखेगी और दिखेगी नहीं, sorry, so that's not the right word. कैसी सुनाई देगी? I mean, how would you be able to hear and differentiate it? Right. So it's going to be a pitch higher, right? And brace your ears, Sumer, that's right. And because it does not stop here, I will go all the way up to right? So this is, so I'm not going to put you through the entire 5 seconds. So this is 1 kilohertz. Okay, this is 1 kilohertz of tone, and you would be familiar with what sinusoid looks like, but this should be exciting. Yeah, this is what you're hearing as well. Okay, and 8,000 hertz. Okay, so if those of you who are wearing headphones, maybe you turn down your volume, right? And I've been doing this for the entire past week in my home, and you can guess कि थोड़ी बाद मेरे बच्चे मेरे पास आते हैं, बाबा ये क्या हो क्या रहा है, right? And so here's what 8 kilohertz is. Okay, so this is 8 kilohertz. So the pitch is higher, right? All right. So this is 18 kilohertz. Okay. So who's going to tell me what this is going to sound like? Saad? Crickets? Saad said crickets. So let's see what it sounds like. Right. So how many of you were able to hear the sound? Did anybody hear it?
Yes, sir.
You
Right.
said it was audible.
It was audible. Yeah, so see,
फिर बहुत थोड़ा सा यानी कि मतलब
okay, very nice. So you see, this is one of the tasks in your lab. So I am 40 years old now, right? And I am what you would consider middle-aged. And this is a tone test that audiologists or doctors do to test your hearing. Okay, so they do it to test your hearing. And as you age, so your ability to hear higher frequencies actually goes down, right? You lose your hearing for high frequencies as you age, right? So I'm going to play it again, Alpha, just give me a minute. And typically humans can hear from 20 hertz all the way up to 20 kilohertz, right? When they're young, all right? Like as you age, so I was able to do this tone test on myself, and 14.5 kilohertz is where my hearing stopped, right? Approximately, right? And I would actually share another video maybe, or वो यानी और लॉरेल वाली वीडियो किसने देखी है? Right? That went viral a few months ago, right? So you see, I mean, everybody's ears are sort of different here, right? So that does not necessarily have to do with age. I mean, we were able to experimentally verify within our family. It has nothing to do with age, as some people hypothesized, but this tone hearing does have to do something with it. So I was not able to listen to this 18 kilohertz tone at all, right? So I'm playing this again. Right? Who heard it? Haris heard it, right?
Oh my God, I can't hear it.
Right. Okay. So if you can't hear it, I mean, right, that doesn't really matter. I mean, this was not the purpose of this experiment. But anyway, so we're going to do this. This is lab task 1, by the way, and maybe we can put it up and see कि कौन कहाँ तक सुन सकता है, right? And let's try to have a competition, if you will, which has nothing to do with age anymore. Okay, so Abu Bakr, you can't hear it? All right, so that gives me some relief at least, right? So right, so we each and every one of us can do a tone test, as we will, using MATLAB, and that's the best exciting part of it. I mean, you will be able to use MATLAB to do this. What you would have to do and you'd have to go to an audiologist to do this. You do it on your own, right? With MATLAB. Okay. Anyway, let's go ahead. Now, here's the point. I mean, so what I'm coming to next is that analog signals versus digital signals, as we talked about at the very beginning, right? So, and since we're dealing with MATLAB as a platform for processing, I want to talk about how you deal with signals in MATLAB, and that's where this entire analog to digital conversion process is going to be, right? The first thing is many real world signals are continuous, and I have this inside the brackets, which are not all, but let's just start with this one, which is many real world signals are continuous, right? And this speech signal is the simplest example of that, right? Speed signal, if the pressure waves at a particular point in time as a function, particular point in space as a function of time is continuous in the sense that the physical time is continuous, and you're plotting that variations in pressure as a function of continuous time, right? So since physical time is continuous, most real world signals are continuous as well, right? But if you're trying to deal with such problems in MATLAB, for instance, or for a computer, yeah, I mean, there's one problem that comes to mind immediately, right? Who's gonna try to identify what the problem is, right? Sumer, you have your hand raised from before, or since you have your hand raised, so do you foresee any problems of dealing with continuous signals in MATLAB? What do you think?
Can you repeat the question? I had my hand raised from before.
Okay, so the question is, okay, do you foresee any problems of handling continuous signals in MATLAB?
Data storage issues, memory, there won't be
Okay,
much
so
space
you
to
would run
store
into storage
that much.
problems, and as Aisha, thank you point it out as well. You would run into storage problems. Give me a minute. Am I recording? Oh yeah, I am.
Yes, sir.
Okay, so you would run into storage problems. I mean, you won't be able to handle, or the computer won't be able to handle this infinite amount of data. So this essentially is infinite amount of data, because time is continuous, and you would have to have infinite amount of data points to be able to handle this, right? So the processors or computers do not have the capability to store infinite amount of data and to handle infinite amount of data. Even if there was infinite storage, I mean, how would you even process infinite amount of data, right? So you would have to do something here to be able to process them, these digital signals. What is that? That is analog to digital conversion, right? And how does that analog to digital conversion work? That works through a process called sampling, right? And in order to illustrate what sampling is, let me just pull up a demo or an animation that I made in MATLAB, right? So this is in MATLAB, okay? And I mean, just to give you an idea of the kind of things that you could really do in MATLAB, right? So can you see my MATLAB screen, everybody? Right?
Yes, sir.
Okay. So here it goes, right? So it not run. Okay. So you see, this is the actual signal that I had to start out with. Right? So this was the analog signal. Let's say this was the analog signal that I want to work with. Okay? So this is an analog signal that I want to somehow store in my computer. Okay? And this is something that I will not be able to, because this would require an infinite amount of data. So the solution is something called sampling, right? And this is how sampling is going to work. Okay, so this is something going wrong. Oh, sorry. Right. So this is how sampling is going to work. So hopefully you're going to be able to see, right? So at time 0, you don't have anything, right? And what you do is that at time 0, you just sample, you switch your switch on, and you just sample what your data was, right? At time 0, this is the red point that the signal was. And then the computer does not know what happened anyway. So in this, all the while from 0 to 0.5 seconds, the continuous time signal or the continuous signal actually varied, yet your computer was not able to gather that information, and it just is unaware of what went on, right? And then at 0.5 seconds, it closes the switch again, right? And it stores some data. You see, at time t equals 0, you store data 0.15. At time t equals 0.5, it stored data 1.21. right? And it goes on, right? So now from 0.5 to 1 second, the computer did not know anything at all what happened with the continuous signal, with the analog signal. And in 1 second, it once again has a sample, right? And then at 1.5 seconds, it has another sample, right? At 2 seconds, it has another sample. At 2.5 seconds, it has another sample. 3 seconds, and so on and so forth. So, and this will go all the way up to 5 seconds, right? And this is where your last sample was stored, right? So that actually continuous waveform that you had is no longer continuous as far as your computer is concerned, as far as your MATLAB is concerned. And instead, what MATLAB has access to is instead these samples, these red samples. कि यार 0 पे क्या sample था, 0.5 पे क्या था, 1 पे क्या था, 1.5 seconds पे क्या था, and so on and so forth. So it's missed out on all of this information within 0 and 0.5 seconds. And from 0.5 to 1 second, बीच में जितनी भी values हैं, उस पे it doesn't know what had went on. And all it has is samples or some glimpses of what actually went on. Okay? It's just like you're closing your eyes, right? And somebody's doing something, and then every 0.5 seconds you open your eyes and see what happens, right? You don't have the entire scene, but rather you have glimpses of that scene. Okay? It's like a video going on, और video के हर आधे सेकंड के बाद आप उसका एक फ्रेम निकाल देते हैं, ठीक है? और आपके पास आखिर में video frames हैं, you don't have the entire video itself, right? So that's the process of sampling, right? At the end of the day, when the computer or the ADC, this is called the analog to digital conversion. When you have sampled, at the end of the day, what you have access to, or the computer has access to, is an array of amplitudes. And corresponding to those arrays are the time instances at which those samples were taken. Okay? So if I go back to my slide, okay. Right. So you can see the slide, right? Hassan, can you give me a thumbs up? Can you see the slide?
Yes, sir.
Okay.
Yes.
Right. So this is the way you convert or you obtain signals in MATLAB is through something called sampling. So these values, these regularly spaced values, are acquired and stored. Now there's some important parameters here. There's important parameters which are, this is something called a sampling time. So this is the time duration between two adjacent samples. So that's called sampling time. And there's something called the sampling frequency, which is just the inverse of that sampling time. Okay? So for this particular example, what is the sampling frequency? Basit, 5_Basit AB. What do you think is the sampling frequency here?
2.
Right, so we have the answers in the chat window. So the sampling frequency is 2 Hertz. Thank you. Okay, so the sampling period is, or sampling time is 0.5 Hertz. We have a sample every 0.5 Hertz. So that means in 1 second, you have 2 samples being transferred to your computer. Okay. All right. So in MATLAB, so for example, you don't really know what the continuous curve was. Instead, what you have is these stem plots, right? These are the red samples that you would ultimately get at the end of the day in MATLAB when you're sampling that audio signal. Okay. And this signal actually corresponds to this data, right? So this is this X, which is the amplitude data, right? Which is amplitude data, and this is the time data, right? This is the time data, which just illustrates that, yeah, at this time, ye sample tha, at this time, ye sample tha, at this time, ye sample tha, and so on and so forth, right? So there's a correspondence between the two. Now, can somebody just quickly tell me, if I were to write this T out in MATLAB, right? Can somebody say, tell me, some one-line statement which can specify this array? I'm going to go at the end and see. Ali Shirazi?
Yes, sir.
So can you give me a MATLAB command which is going to give you this T vector, one-line statement?
Sorry, but sir, I didn't understand your question.
So ये T आपको T नजर आ रहा है आपकी screen पे?
Yes, sir.
Right. So if I were to specify this in MATLAB, how would I do it?
Sir, create a matrix.
How do you create that matrix? So it's linearly spaced, right?
Yes, sir.
So we've done this in lab 1.
So, sir, we will use the line space command.
Okay, that's fine. You can either use line space or len space, or there were many correct answers here. Zazan, thank you. So this is 0 colon 0.5 or so, colon 7. So actually 7, yeah, 7. Okay, so it's going to 0 colon 0.5. This is what it's going to do. So MATLAB script, we just write it out, is you just specify what the sampling instance is, sampling period is, which is 0.5 seconds, and then T is 0 colon TS colon 7.0. And it will automatically give you this entire vector. Okay? And you would say, I would have said 0, and then I would have typed 0.5, and then I would have typed 1.0, and then would have typed 1.5. That would have worked as well, but that's too cumbersome, right? Because what if this was from 0 to 100 seconds, right? I mean, it would be very unfeasible to write them explicitly out. The MATLAB script we would use is 0 colon TS colon 100. Okay? So MATLAB allows you to do this, some sort of deal with sampling very nicely. There were some answers here in the chat window which started from 1. That's not true because I start from 0. Okay? So it should start at 0. The left extreme is 0. The right extreme is 7. The lower extreme is 0. The upper extreme is 7. Okay? All right. So here's the entire ADC process. Okay? You have a real world continuous signal, which for example is speech, okay, which is analog, which is fed into an ADC. And that ADC just gives you this sample or an array of data, okay, which is a digital form. And the ADC is controlled by something called the sampling frequency, which you can control, with the short trick can control, right? And the ADC, you have ADCs on board your computer, by the way. Okay? You have ADCs on board your cell phones, by the way, as well, right? And many other equipment that you have, right? So that ADC, for example, is on your sound card, on the PC sound card, which has a microphone. Microphone gives out an analog voltage signal, which is fed into an ADC, and that ADC spits out this digital data, which you can use in MATLAB for your processing. Okay. Sound card, Hussein, is what plays your sound, which is connected to your speaker, which is basically a card that actually goes into your laptop or your PC, जिसके अंदर microphone लगा होता है, जिसके अंदर speaker की output लगी होती है, जो आपके सारे jacks लगे हुए हैं, right? Those are actually connected to something called a sound card. Okay, audio jacks are connected to something called a sound card. Okay, now, what is the answer to this? I mean, and if you know what sampling is, if you know what ADCs is, the question is, do we lose information by converting to digital? Can we go from digital back to the original analog signal? And how is the information loss, if any, related to the sampling frequency? So what do you think is the answer here? I mean, you're clearly up from 0 to 0.5 seconds. I don't really know what went on, right? Signal isna ja raha tha, niche ja raha tha. There's no way for the computer to know what goes on, right? So yes, Salman, go ahead.
For the first question, I can say that information will be lost.
Okay.
For the second one, I don't think we can go back precisely to the input, but we can go close to it if we increase the sampling frequency.
Very nice.
Or reduce the sampling interval time.
Okay, very nice. So that's all the intuition that I would like to stick with. I mean, there's a strong mathematical theory behind it, which tells you, okay, you can actually go back to the original audio signal if certain conditions are satisfied. But let's just not go there. I mean, let's just stay intuitive, and that intuition exactly stops at what Salman said. And in order to illustrate that, can we go back from the digital back to the audio? Let's consider an example, the same example, right? So this is that same example that we saw earlier, but rather, so with the sampling frequency of 2 Hertz. So there are 2 samples per second, right? Now, if I were to, so the blue dash signal that you see is the original audio signal that you had, right? And these circles that you see are the samples that you were able to collect on your sound card, or the sample that MATLAB was able to collect, right? Now, if I were to reconstruct the analog signal from these digital signals or from these circles, what do you think? I mean, किस तरह करें? I mean, सबसे पहले जेब में क्या आएगा?
Dot to dot.
Yeah, Mariam, go ahead.
Dot to dot connect होंगे.
Exactly. How do you connect dot to dot? You're right. How do I?
Straight lines.
Straight line. Excellent. Right. So that's the first thing that comes to mind. Right. And that is something called, there's a name for that. And there's that name is linear reconstruction. Right. So you have two dots, two adjacent dots, you just connect them linearly. Right. And the reconstruction that you get is what you see on your screens here, which is not a very good reconstruction. Okay. So this is linear reconstruction. But for 2 hertz, you can clearly see that the reconstructed analog value is not very, very close to what the original signal was. And if I increase, so as Sumer said, depends on the sampling rate. Yes, it does. So if I increase to 4 hertz and then I connect the dot to dot, right? So once again, this is the linear reconstruction, and it's clearly visible that this dot to dot reconstruction or linear reconstruction is quite close to what the original analog signal was, right? And I can increase this even further. Let's do it at 8 hertz. And at least visually speaking, this linear reconstruction method that we've devised on our own, right? So, we've been able to get a very, very good approximation to the original analog signal. Okay? And by the way, I mean, you should, maybe somebody had this question already. How does the plot command work in MATLAB? I mean, you would have done plot in lab 2 a whole lot of times, right? तो वहां पे आपके पास एनालॉग सिग्नल तो कभी हो ही नहीं सकता, right? MATLAB में कभी एनालॉग सिग्नल हो सकता है? No. I mean, all of the data that you had for COVID-19 on each and every one of the days, or the death rates that you evaluated for each and every one of the days, that was a discrete data in the sense it was not continuous. It was evaluated on one day and then the other day. बीच में क्या हुआ? You don't know, right? But you were able to get a continuous plot out of it through the plot command. And this is exactly what plot actually does. The plot actually sees the adjacent points and draws a straight line between them, right? So that the plot command does a linear reconstruction, if you will, visually speaking. Okay? So that's an important point to consider. Okay? So based on what we saw here, going from 2 hertz to 4 hertz to 8 hertz, this is an intuitive answer that I can come up with, which is if sampling frequency is high enough, we've been able to see that the original analog signal can be reconstructed from the digital signal quite accurately. And this is where we're going to stop as far as our intuition is concerned. Mind you, I know that this answer may actually lead to many more questions, right? And those questions is, what do you mean by high enough? I mean, what is high enough? Is 4 hertz high enough? Or is 8 hertz high enough? Or maybe 16 hertz high enough, right? I know that's a valid question if you have that, right? Similarly, when you say quite accurately, what do you mean by quite accurately? I mean, this is not really a scientific term. I mean, quite accurately is not scientific, right? And can it ever be 100% accurate, right? So it turns out that there are very, very scientific answers to these questions, right? There exist scientific answers to these questions in a theory which was developed, to maybe surprising to you, more than a century ago. Okay? Or the 1930s mein jaake, I mean, was sort of formalized, or 1940s maybe jaake log karte rahe. But it originally started out in 1930s or 20s, and people were able to develop that theory, mathematical theory, to try to identify what is high enough, right? How high does it have to be for you to be able to reconstruct that signal in 100% accurate fashion? Okay? Are there other methods in linear construction? Yes, there are, but we're not going to go there. Okay? As far as W100 is concerned, this boxed answer that you see here, this is going to suffice for us. The original signal can be constructed with this signal quite accurately if we have a high enough sampling rate. And all of the examples that we're going to see in the subsequent labs throughout the semester will satisfy this high enough quantity. Take a high enough property. Okay? Right. So this is digital to analog conversion, right? So what we've actually seen is something called digital to analog conversion. So you have digital signals in MATLAB, and if you were to convert it to analog, one of the ways to do it is just do a simple linear reconstruction. Just connect the lines. and or maybe employ some other methods. And your sound card is once again a digital to analog converter. In the sense कि आप जो audio play करते हैं अपने PCs के ऊपर या on your iPods or your smartphones, right? Whatever music that you hear, that's actually digital data. And yet what you hear is analog sound. And the way you hear that analog sound is that digital data passing through something called a digital to analog converter, which does some linear reconstruction or something more sophisticated than linear reconstruction, okay? And then converts it into an analog waveform which you can hear, right? And that sound card is once again governed by the sampling frequency, which is controlled by software. And we're going to see how we can use MATLAB for this. And the lab tasks, there are more details there. What does it mean? Sampling frequency. How does the sound vary when you change the sampling frequency and so on and so forth. Okay. So here are the lab tasks. This is probably the last slide. So there are 5 lab tasks here. One of the things that we wanted you to do was to record your own voice in MATLAB, and MATLAB allows you to do that. However, we found out that MATLAB online has some sort of problems accessing your microphone. So we've skipped those labs. However, the code is there in the lab handout. So if you want to try it out, and if you have if you have a desktop version, you can download it if you want. If you have that already, you can run that code and record your own voice and have fun with it. Okay. So the tasks are very simple. The task 1 should not take you too long. It's just a pure tone test that we talked about, right? I stopped at 14.5 kilohertz. Let's see how much further that you can go. All you have to do is generate a sinusoid and you play it with your sound, with your speakers, and see where your hearing stops. Okay, and the commands for that, all of that is there in the lab handout. Okay, the other task is we were going to give you the second task. We're going to give you some recorded data, which is my own voice, and you have to play a different sampling frequency to try to observe what happens when you play it at a sampling frequency which is not the same as the sampling frequency at which this was recorded. And I have the results for you here. So. Right, so this is Shrek Urdu Mutsim. Okay, so what do you think happened here? One of the points I do want to mention here is, remember, this is a class going on, right? So you want to make sure that your comments here are suitable. Okay, so some of the comments I don't like. I mean, this is not a joke. Okay, right? I can name some names here. I don't want to. Okay, so please be serious here. Right. So this is the sound played at a different sampling frequency than what it was recorded at. Can somebody tell me what is different here? I mean, this is played out very slowly, right? So why is it played out very slowly? I mean, what's actually the underlying principle? And it's okay if you don't get it right now.
Can I speak? Hello.
Yeah. Oh, sorry, Vikas. Go ahead.
Yes, sir. So इसके अंदर ना टाइम फ्रीक्वेंसी जो है चेंज करी है, वो जो हमारी पिछले वाली साउंड थी जिसके अंदर बिल्कुल क्लियर हमें प्योर टोन आ रही थी, उसकी जो फ्रीक्वेंसी थी वो ज़्यादा थी, तो इसके अंदर हमने सैम्पलिंग फ्रीक्वेंसी कम कर दी है, टाइम पीरियड कम हो गया, इसलिए जो आवाज़ है वो भी
Excellent. And that's the correct answer. That Basit also has the correct answer. Mariam also has the correct answer. That's actually true. And what you see here. So it's the other way around. I mean, so now it's a higher sampling frequency, and you can observe the effects. And why does it go shriller or it go coarser? I mean, that's something. Let's try to brainstorm on what that is. The task 3 is about playing the sound backward. There's just one command that you have to do, and just see what happens. And this may sound demonic. Right. So even though this does not have any hidden message here, the sound that the voice that we've uploaded on LMS, that actually contains some hidden message, right, in there, which you will only be able to hear correctly when you play it backwards, right? And this is reminiscent of some conspiracy theories that I mentioned in the handout as well. In my youth days, the Freemasonic conspiracy theory, saying Michael Jackson put songs there, you playing backwards, you'd hear something about 666 and devils and whatnot, right? So in light of that, I've embedded some hidden message there, which you would have to find. The task 4 and task 5 may be a little bit more. Task 1, 2, 3 are very simple. This is just creating a clipping effect.
प्यारे बच्चों, मेरी आवाज सुनो और सुनते चले जाओ.
And you may not have been able to hear it very well, and the reason is there's a lot of distortion here because of clipping. And what is clipping? Clipping is कि आपके जो electronic equipments होते हैं, they actually do this, introduce this clipping noise. It's called Hania, it's called clipping noise. And if the amplitude goes above a certain threshold, it just clips it, right? Saturation हो जाती है electronic equipment में. And because of that, you will hear clipping noise, clipping effects, and that's just trying to replicate what that clipping effects would be with in a digital form. Okay. And finally, are echoes or reverberations. So how is reverberation? What is an echo or reverberation? Ali Shirazi?
Sir, I wanted to ask, why does the electronics clip the sound?
Okay, so that has to do with some electronics which that's perhaps beyond the scope of this lecture. Okay, analog electronics सोच हम पढ़ेंगे तो फिर then we will be able to figure out कि उसकी supply voltage कोई होती है, supply voltage से ज़्यादा नहीं हो जा सकती, ठीक है, and that's where things are clipped out. Okay. Or reflection of sound, Mariam, good. So reflection of sound is echo. An echo is कि मैं कमरे में बोल रहा हूँ, right? So you hear my voice on a direct path, right? Speech, and then there are other reflections from other paths all over the room, right? And they reach you with a different delay and a different attenuation. And you have superposed copies on top of one each other where the copies are delayed versions of each other, and that creates something called echoes, or that creates something called reverberations. And this is something that you're going to try to replicate in MATLAB. So MATLAB is going to allow you to create that effect, create those digits. Somebody said in the chat window, which was, would we be able to become a DJ after this? Yes, so you will be able to at least create an echo effect in your own voice or something that you've created, right? So this is an echo.
प्यारे बच्चों, मेरी आवाज सुनो और सुनते चले जाओ.
Okay, so these are echoes, and this is something you're going to have to create. Now, you may figure out these are so many tasks, 5 tasks. The first 3 tasks are very simple. We should hopefully be done with them very quickly. The last 2 may take some bit of time because there's some mathematical processing there, and we want to be comfortable with at least some sort of mathematical manipulations. And so, Mary, yes, there's no MATLAB on ramp this week. Maybe in the next week we can have some exercises from there. Okay, so this wraps up my discussion. Once again, this is seeking help. The 5 Zoom meetings are going to be active at the same time, 4 TAs, and this meeting is going to be active not all the way up to 6 o'clock this week. So 6 o'clock तक बाकी 4 meetings for the TAs are going to be active, but I may leave at around 5 p.m. I guess. So I'm going to stay here for another hour if you have any questions. Otherwise, we're going to be on LMS chat to help you as well, right? So you go ahead and download that lab handout, which we've spent lots of efforts in creating. You can go ahead and give it a read, do the lab tasks, and talk to us if you have any problems. Is there something the TAs want to say? If I missed anything? So there was this point about late submissions. I mean, we get a feeling that people are delaying their submissions right up to the end, and so we want to discourage that as much as possible. And from next week onwards, we will have some penalties, if you will, for late submissions, in order to be fair to those people who are doing their submissions on time. Okay, so we're going to formally announce that policy over the weekend itself.